When a high-voltage breaker attempts to close on an unverified circuit, the result is an instantaneous, catastrophic arc flash. The physical stakes of bringing a Substation Automation System, or SAS, online require absolute precision. A single logic error at the control level becomes a physical disaster on the grid. To eliminate that risk, commissioning cannot be treated as a random checklist. Training Module 17 dictates a highly stratified 20-test algorithm. We progress sequentially from foundational prerequisites up to full automation logic, proving the integrity of the system at every distinct stage. This animated diagram illustrates the substation validation architecture and test strata. It serves as our map for the entire commissioning sequence. The structure is built across 5 distinct layers, starting at the physical foundation and rising through the communication nervous system, the localized brain, the field senses, and finally, full system verification. Focusing on the base, Layer 01 operates under a strict reference framework established by the IEC, IEEE, and NEMA. When project specifications, manufacturer instructions, and these standards conflict, the governing rule is absolute. The most stringent approved requirement always takes precedence. This brings us to Test 17.1, the prerequisite phase. Absolutely no physical testing begins until strict boundaries, lockout, tagout procedures, and cybersecurity access approvals are established and verified. Enforcing this foundational discipline isolates variables and prevents compounding errors. A missed safety boundary or unverified credential at Layer 01 guarantees a phantom failure when we reach the complex logic at Layer 05. This workflow diagram details the specific documents required to clear Test 17.1. The PM engineer and CSD technician must physically locate and review the factory acceptance test records, IP address lists, approved SAS panel drawings, and all cyber and access credentials. With the paperwork secured, the team executes a rigorous physical inspection of the SAS panels. They trace the readiness of servers, Ethernet switches, GPS clocks, and power supplies, documenting every condition before proceeding. Once the inspection is complete, we hit a mandatory hold point. The client and the commissioning engineer must physically sit down, review the entire evidence package, and manually sign the document to authorize the next phase. The criteria for this sign-off are exact. The signatories verify established test boundaries, confirm physical results against approved references, capture specific alarm evidence, and ensure total equipment restoration. This rigorous hold point sign-off happens for every test in the sequence, from 17.1 through 17.16. To accelerate our journey through this architecture, we will represent this repetitive paperwork loop with a standardized visual shorthand, an automated checklist clearing the screen as each technical demonstration wraps up. The hold point is a hard, audited firewall. It guarantees a verified baseline state of safety and security before we introduce live voltage and dynamic variables into the system. This diagram shows our ascent to Layer 02, the communication nervous system, initiating Test 17-2 for SAS fiber-optic cable testing. We begin with thorough physical checks. Technicians verify core numbers, trace cable routing, check bend radiuses, and rigorously clean every optical connector before any laser is introduced to the line. This technical reference details the insertion loss budget. For 850 nanometers, the baseline limit is the length in kilometers multiplied by 3.5, plus loss values for coupling points and splices. If exceeded, an OTDR trace pinpoints the failure for repair before retesting. With the fibers verified and safely capped, the hold point clears, and Test 17.2 is complete. We immediately jump up to Layer 04, the field senses, to execute Test 17.3 for peripheral devices and Test 17.4 for live SAS measurement testing. This schematic diagrams Test 17.4 safety. Technicians isolate live circuits, injecting voltage and current into bay control unit terminals, never opening current transformer secondaries. Injected values must map perfectly. We verify scaling and polarity to ensure local BCU data perfectly mirrors remote SCADA displays. These physical validations are the bedrock of system accuracy. If an inverted phase polarity or a degraded fiber splice passes this layer undetected, the automation brain will later act on false intelligence. This architectural view brings us into layer 03, the brain of the system. We execute test 17.5 to validate the engineering workstations. This configuration guide details the rapid confirmation of the EWS hardware, operating systems, patch levels, and cybersecurity protocols, ensuring right privilege access controls are strictly enforced. This hardware diagram highlights layer 02's test 17.6 requirements. We run rapid ping tests across Ethernet switches to confirm management IPs and MAC tables. We verify spanning tree protocols and ring topologies, ensuring switch health alarms transmit directly to the SAS event log. We move immediately into test 17.7, redundancy testing, simulating hard component failures across the network pathways. We record exact millisecond failover switchover times, ensuring data continuity remains intact and no operator control is lost beyond the approved safety limits. Transitioning to test 17.8, we evaluate gateways, confirming precise protocol mapping and flawless data transfer from the SAS out to external SCADA control centers. Next up is test 17.9, GPS testing. We confirm perfect time synchronization across all servers, workstations, and IEDs, so every digital event shares an identical clock. We simulate a hard loss of the GPS antenna signal, observing the system's holdover behavior, monitoring alarms, and documenting time drift before restoring satellite lock. Normal topologies are restored. The visual shorthand triggers in rapid succession, clearing the hold points for tests 17.5 through 17.9. While these IT protocols are standardized and fast to execute, their redundancy and microsecond timing form the unbreakable spine required for automated decision-making. This reference guides test 17.10. We scrutinize the intelligent electronic devices, the localized brains at the switchgear, confirming firmware IDs and network names. We simulate analog and binary inputs into the IED, tracing them to confirm correct alarms and sequence of events reporting. We then verify the IED's internal disturbance and fault recording functionalities, ensuring crucial forensic data is accurately captured and accessible after a simulated grid event. The sweep continues through tests 17.11 and 17.12. We confirm all maintenance laptops are rigorously scrubbed of malware risks and verify the operating workstations properly handle alarm viewing and operator usability. For test 17.13, we conduct the final panel inspections, ensuring all physical cabinets across the substation have verified wiring continuity, proper grounding, and active ventilation. This server hardware diagram illustrates the final step in the hardware sweep, test 17.14. We verify the SAS servers, confirming database integrity, the health of background services, and the ability of backup clients to seamlessly reconnect after an interruption. The documentation is signed. The final batch of visual shorthand hold points cascades across the screen for tests 17.10 through 17.14. The physical infrastructure, every fiber cable, every Ethernet switch, IED, and server is now 100% physically sound and communicating. The stage is set for the ultimate proof, validating the automation logic itself. This architecture diagram shows our arrival at the absolute peak, layer 05, system verification. With the entire structure below fully verified, we can safely test the automated logic. This conceptual diagram maps out test 17.15, taking the SAS on a complete end-to-end flight test. We move from the switchgear out in the GIS rooms directly into the command centers. Technicians generate a simulated digital signal in the field using an ASE 2000 tool. We trace that exact signal as it routes through the SAS processing blocks, confirming it displays with absolute precision on the operator's HMI screen. We systematically verify alarm priorities, check the scaling of timestamps, and monitor the logic's behavior during deliberate communication interruptions to ensure the system handles data loss safely. This interlocking logic diagram illustrates the final and most critical phase, test 17.16. Overall, interlocking is the ultimate safety net of the electrical grid, dictating what physical actions are permitted and which are denied. We prove the logic by simulating a safe operation. We verify the command is accepted, the output is issued to the equipment, and the correct feedback populates the HMI. Then we attempt a deliberately unsafe operation, such as commanding an earthing switch to close while the circuit breaker is still fully energized. The SAS actively blocks the unsafe command. It denies the physical output to the switchgear, generates a specific alarm, and logs the error event. The system successfully prevents a catastrophic physical fault. With the logic proven, we clear the final hold points. The punch list is closed, and we execute the final restoration, removing all simulators, test bypasses, and temporary accounts. By sequentially validating the foundational physics, verifying the IT communication pathways, and stress testing the automation logic, the Substation Automation System is now fully approved. The electrical grid is secure, integrated, and ready to energize.